Mike Shub. It's a pleasure to have you here.
Okay, I'll try. So a computation is more or less a finite program. So you've got some, we like to call them machines, and you've got some input, and then you have this finite diagram that might, over here you compute something, compute maybe plus, minus, times, or maybe you'd apply a differential operator depending on what structure you're talking about. So for me, it could be mostly it'll be a ring like Z or Z mod 2, or the real numbers or the complex numbers, maybe the rational number. So then you compute something, then you might go, so this is like an instruction, and then you can go to some other type of thing, you might branch. And then depending on the type of structure that you're talking about, you might branch on equal to 0, or not equal to 0, or bigger than or bigger than 0, or less than or equal to 0. So you do some computation, you look at some output of your computation at some component, and they say, does it satisfy these properties? And then you go to other possible instructions, and maybe your instructions say go back here and then compute again and go through, and you may have some loops, or you have a finite diagram. And finally you get to some node and you output something. So what's the input? The input, and this is going to be important, is going to be a finite string, but of arbitrary length. It can get longer. So the input is some x, an x1, an xn, and then n is an element of the natural numbers. That's important because this makes the computation uniform. So if you're computing determinants of matrices, for example, you have to compute n by n matrices. Your program has to compute the determinant of n by n matrices for every n. And then inside the machine, you can imagine that instead of representing the input this way, you think of it as having an infinite number of zeros, like the direct sum of the algebraic object, so that you can do computations and move things in and out, put new things. So you've got added space, but of course it costs something to write, so you have to compute something and put it there. Okay, so this is the states. The states are, after you've done some computation, maybe here I had some particular f in mind, and I put f prime of x, f of x over f prime of x to compute the Newton state. It's an iterative process. Yeah.
So it's a finite string of things.
Yeah.
What are the things?
So the things are elements, as I was saying, of it could be in a ring,
Yes.
or a field, or something more algebra, or some algebra, differential algebra.
Not necessarily finite, and more likely
They're
to be-
always finite. They're always finite.
The strings are finite.
No, I understand, but the things are not finite. I mean, this, yeah.
The machine is like, it's like a Turing tape. The tape is infinite, so you could put things in any place in it, but you have to shift it over and do that. So the interior of the machine gives you the possibility of putting arbitrary long things there.
There'll be real numbers.
They will be real numbers, yes. So largely we're dealing with the real numbers, the complex numbers. Z or Z2, Z2 gives you back the classical theory.
Turing stuff.
Turing stuff. So, and Z, if you put the bit size on the input, you have to tell you about the size of the input. And then the branching for the field, it depends if the field's ordered. So here, you branch on bigger than 0 or less than or equal to 0. And here, you don't have an order. You branch on equal to 0 or not equal to 0. So then, you want to do a computation. Maybe you want to compute e to the x up to relative error epsilon. So you input now, you would input epsilon, and you did x and you say, I want you to write a program to compute e to the x up to L square epsilon. And so then you write one and you do it. So then there's this question of the input size and the cost. So the input size, in this case, is most of the time just going to be the dimension. Input size is dimension. In this case equals n usually. And then there's the question of the cost. The cost is the time it takes to compute. So I'm only doing one operation at every moment here. So if I input an x, I see if it outputs, and I see how long it took to output. So the normal time, of course, usually time to output. That's just, in this case, the way I've made it here is the number of operations, either branch operations or multiplications, additions, divisions that you've done, because you do one in each place. On most, or maybe even including, well, if you have this loop, you're not doing that, but you're, this should have looped this maybe. I can't have a loop and also, unless it's a branch. Unless it's a branch node, there's only one exterior arrow. So, and then there's the question of the polynomial class of computations. And those are the class of computations where the cost is polynomial on the inputs. So you have a problem like this one, and you ask, can I compute this one in polynomial time in the input? And maybe I have to do something that maybe vary the size here because the epsilon might be a variable. So I may have to give you a different notion of size. Maybe I'll add the log of epsilon into the input side for this particular one. Or I could ask you as an integer even. And, well, I don't know, you compute that in polynomial time? Anyway, this polynomial class is a tremendous class because it's very robust. So if you're trying to make a complexity theory, you want a notion of a problem being polynomial time. It shouldn't depend exactly on the machine you've made or on the very small details of the program. So it could be, for example, a random access machine, or it could be a Turing machine. It could be various different types of machines. Turing machine might have to pay for the moving the tape back and forth. So that would add maybe an n squared to your cost because it takes time to move it back and forth, read everything. Well, you see that wouldn't matter for polynomial. N squared is still a polynomial of n. So it doesn't change the class. So this is actually a great discovery to focus on the class of polynomial time computable functions. So then there's a special so this is, I would say, this is already as it is the input size and the polynomial class. It's a good notion for exact computations. So in these rings, I'm assuming you're doing, for the moment, you multiply two numbers, you multiply them in the ring at cost 1, independent of what elements they are of the ring. There's no cost that's dependent on the size. And you get an exact answer. This is exact arithmetic, and this exact arithmetic, a special class of functions are decision. This is usually where the polynomial class is discussed. That you're now given some subset x in this possible state space, let me just write, this is the direct sum of the ring infinitely often. The ring or the algebra or whatever you want to put there. And you now ask, given an input, x, so that's an input, size n, is x in x. That's a decision problem. So in other words, you're trying to compute the characteristic function of the set x. And so this decision problem is said to be in P if you have a polynomial time computation for the characteristic function of the set. So there's another class called NP. And NP is usually just only refers to decision problems. You say a problem X is in NP if there exists an auxiliary variable Y. So I need this auxiliary variable Y in a machine and a computation. Such that if X is an X, there exists a Y such that this new computation terminates the polynomial time on xy. On this pair. And gives the right answer. Yes. For x and x, and doesn't give yes for x not x. So it gives the correct answer, but you get an auxiliary piece of information, y, in order to do the test on whether or not x is next. So what's the prototypical example that we like best is that you take a family of equations. The way it says this family of equations have a solution, and for that you'd have to do some complicated computations. Maybe Hilbert-Snell-Stellensatz tells you how to do it. It's give you an exponential time algorithm for deciding. You can decide that question over the reals or the complexes, and it takes a long time. But if someone tells you the zero, you can go and check it. So that's the y. So y would be the solution of the problem, and you just go and check it. That's an easy computation, just evaluate the polynomials. You can do the same with any structure. And if you have differential algebra, you can just certainly ask the same type of question: is there a solution? So now the big problem that Cook and Steve Cook, so I think it was a guy by the name of Edmonds who isolated this polynomial class. And then I think Steve Cook who made the relationship between P and NP. So the problem that arises from Cook and Karp's work is that P equal NP. That would be, if that were true, that would be amazing. So all these problems that would seem difficult to compute by any deterministic way we know would turn out, if they could be checked non-deterministically, would then have an easy computation. So it would be shocking. But yet it's an open problem. This is an open problem. And either for R with inequalities, or C with equality, or Z2 with equality. These three cases are open, and how do you sort of analyze them? Well, you try to make what's called an NP-complete problem. NP-complete problem is the problem that is in P, it's an NP, and it's in P, even only if they're all in P. How do you get an NP-complete problem? Well, there's kind of a natural a way to go and produce an NP-complete problem is just you look what the machine does. So you say, what does this machine do? I'm going to write down a family of equations that explain what this machine does on an input. And if the machine is an NP, it's going to have an input X, and then it's going to exist a Y, such that this machine, when I write down the equations, next node, next state, next node, next state, next node, next state, I finally come to output, yes, it's a family of equations. So I just say, does this family of equations have a solution? Is there a Y? On input X, I want to know, is there a Y? So it's the family of equations has a solution. So this makes that problem, Hilbert's Stellensatz over the reals or the complexes over Z2 into an NP-complete problem. Take any problem in NP, you say, what will this machine or this program that shows that the problem in NP do? We're going to give an input X, and there will exist a Y, which will make this program terminate in output yes, if and only if X is in the set X. And that means if and only if the system of equations, which takes X as an input, has a solution in Y. So you just write this. So you can find this. This is all in, you can find our book, Blum and it's called Complexity of Real Computation.
Could you clarify? So you mentioned for the equality to have tremendous impact on simpler algorithms. So would you say that this statement is rather theoretical or actually practical?
Well, I mean, for practical, I will speak a little bit about practical. Practical may involve an epsilon. We have to discuss how we'll deal with epsilon. But I think for discrete problems, certainly in discrete computer science theory, it's in some way practical. But on the other hand, practical doesn't mean a polynomial of degree 15. That's not very practical.
Or 15,000.
Or 15,000. Even 15. 15. But 15,000 even worse. So if you produce a polynomial of very, very high degree, what does it mean in terms of actual practice? On the other hand, it means something in terms of being able to make a theory, and it can give you some sort of notion of how things should proceed. It's certainly better, even 15,000 is better than exponential. So,
Really?
so,
Is it better?
Well,
Theoretically,
then you get large.
exponentially better.
When n gets large, So the question is how large n is. I'd say, from what I understand of the actual numerical analysis community, is that they are interested in the leading edge. They want to do the hardest problem. And the hardest problem is as many variables as they can get, and the best precision that they can get to make it work. And they're not interested in, so much interested in what your little calculator will do when you press the tangent button. That's not the leading edge, even though it is a huge problem. I had a guy who worked in my group at IBM, spending a lot of his time making sure that the cosine was correctly computed to the right number of digits. So when you made a new machine, you had to make sure that all these operations gave you the right answer to the right number of predicted digits. You want to get that last digit correct.
There's another hidden problem here. It's the average, because this is, if you do it in a straightforward way, it's worst case complexity. Whereas worst case may never occur. There's a famous, in IBM, there was a famous legend when there was some military-grade computer 30 years ago. They built a super machine, and while testing, they ran linear programming things, which are exponential theoretically, and they never randomly generated. They never the exponential problem. They were all polynomially decidable by the usual simplex method. So it's a big question, and you're asking a very good question.
Yeah.
But there's no definitive answer. There are, as usual, among engineers, there are extremists who believe that all this complexity theory is nonsense. And there are some optimists which believe that there should be some good theoretical background for everything.
So you would say that the primary interest for people to work on this is possibly some theoretical background.
But yes, but as everything has the potential for abuse. You can abuse even mathematics, such a beautiful field, and you can abuse computer science. You can abuse complexity theory.
I can give you an actual thing that happened to me. I was working at Queens College in 1980, something like 1981 or 2, and I think that had bought me a little home computer, so I had a little computer at home. And so I decided to do a couple of experiments. One was a dynamic system experiment. The other one was a kind of dynamic experiment related to the eigenvector problem. I wanted to know power method. Let's take the power method and see how many steps it takes to get to the epsilon of the dominant eigenvector. So I just took 2 by 2 matrices, diagonal, e to the t, e to the minus t. I took a random starting point, and I had the machine, which is, I think, 5,000 iterates, or 5,000 examples, and I asked it to tell me how many steps it took. And then I was sitting there saying, I could probably compute this. So I actually, while the machine was running, I actually computed it, and the answer was the average number of steps is infinite. This is integrating, essentially you're integrating the log. So you have to take lambda to the n, whatever the eigenvalue is, lambda to the n times the starting vector is going to be less than epsilon, so that means n is like the log lambda, and if lambda is going to 0, you're in a lot of trouble. So it was infinite, and then the computer gave me 7. So why did the computer give me 7? I had thought about it. The computer gave me 7 because 2 to the minus 7 was the smallest number at the top, 10 to the minus 7. So it gave me the log, but the best log that it could get given its precision. So I think the answer would be that, well, if you do an experiment and you're happy with the answer, it may change when your computer changes. So you better have some theoretical
understanding what's going on there.
But then, so this is a theory that's a nice theory, I agree, and maybe it doesn't speak so much to practice. I don't know how much numerical analysis would like it. In some states, in recent years, we've been emphasizing average complexity, and then it depends. You may find examples like power method or something where the average would not be infinite, but even there you might find that the pole is very sharp, and you don't tend to find an example where the number is large. So it depends on these little fine things about like what the pole looks like when the number of steps is going to infinity. So you may be integrating some rational function. So we found, and I think, let me say this, we found that we had to introduce, what made sense to introduce a complexity number. So the input size not only had a dimension, but it has a natural complexity notion attached to it. That would influence the number of steps that you would take to solve the problem. And for example, in linear algebra, where they're worried about this epsilon and the error. So let me say something about epsilon and error. If you're doing computations with error, you might want to look at two more things. One is the input, which would be an epsilon, and then you might want to have log epsilon as a new entry to the size. So you take size plus log epsilon. So that's what you want the answer to be. That you're going to have to compute with numbers that large. So if you're going to compute with large numbers, they're going to have a cost in multiplying, especially if it's multiple precision. Numerical analysts hate multiple precision. And if you look at linear algebra, numerically accurate linear algebra, they say if you're going to use multiple precision, it slows down the computation by a factor of 400. So since they're trying to do cutting edge stuff, 400 times is. So,
It's a fast multiplication, I know. Look at it.
so you might want to add log epsilon if you're doing computations up to size log epsilon. But you might want to also add to the input size a condition number. Condition number. And now there are two ways that this might come in. So for a decision problem, this decision problem is going to maybe have a boundary. Maybe the set is the Mandelbrot set. Mandelbrot set. It's got a fractal boundary. And you're not going to be able, with any finite precision arithmetic, to decide exactly. So if you put in an entry, you're going to have to worry about how close is this entry to the boundary, because if this entry really represents everything within epsilon of it, then that might spill over the boundary and you get both types of answers, yes and no. So especially if you're doing computations with error, or with input error especially, then you have to be careful about this distance to the boundary. Another place you might have to be careful is even if you know the distance to the boundary, if the function that you're trying to compute in here, say is an analytic function, but it doesn't converge on the boundary here. So you're trying to compute a function that doesn't converge. You're trying to compute a value near the boundary. You're not going to do that in a finite number of steps because it means you're going to compute an approximation to this function, which is a finite degree polynomial. And you can't. So in some sense, if you're coming closer to the boundary, you'll have to, even in exact arithmetic, spend more time. All right, so that's two things to keep in mind. Now we've got a condition number. The condition number linear algebra was known from the beginning. So this is, Turing mentions it, and von Neumann and Goldstein, they talk about it a lot. The condition number of a matrix is, the norm of the inverse. And what this number tells you is how accurate your input has to be in order to get an accurate answer. So this number k will expand epsilon by k. So your condition of your computation will have to be more accurate according to the condition number. So that was known, but that's because of approximate computation here. Because there's two things you have to keep in mind: the possibility of approximate computation and the possibility that even in exact computation, there is some sort of condition, maybe a distance to a boundary, or if you're using Newton's method, it was, in our case, it was the distance to double roots. So we had a system and a point, and how close is that system and point to a system with a double root? That was a condition number, because Newton's method won't work quadratically. The number of steps will get larger as you approach the general equation. Now we're going to talk about, first of all, just exact computation with a condition number. But now I tried, and I tried with a couple of people to put together the notion of approximate computation and exact computation with a condition number, and when you're computing the characteristic function of a set, or you're computing something like e to the heirs. So these are different types of phenomena, but I wanted to get one definition that would find everything in terms of what is the condition number. So for the condition number for decision problems, you say exact arithmetic should be maybe just the distance to the boundary between yes and no. For other condition numbers, it might be the sensitivity of the answer to the input. So if your derivative is very large of the answer with respect to the input, you may have to specify the input too well, and this will cause me to increase the precision if I'm doing approximate computation, so I have to put in the size of the derivative. But what we found in studying Newton's method is that somehow the condition number comes into play even in exact arithmetic. And between the derivative and the distance to the boundary, I couldn't find a good universal definition. And then Felipe Kuker and Gregorio Maljovic they had a great idea. They just said, let's just consider condition any function. So now they consider an input to a problem is now, so the input is now x in some the structure to the n power plus a function mu. Mu that, or mu of x is some number between 0 and infinity. And now you say, okay, I want to solve my problem polynomial time in the input size, which is now the dimension plus log mu. So the new size equals the old size plus log mu. Now you try to solve things in polynomial time. In this new setting, well, that was great. I was really trying to get something concrete, and they just said, no, let's just go for it. And so then there's a kind of an amazing theorem. So this theorem is maybe some paper of Kuker, some version, and then in Maljovic, I have a paper that's on in the archive. And the theorem is that P equals NP in this situation if it only if it equals NP. The usual situation. NP with U if and only if P equals NP as usual over R. So this was, in some ways that's an amazing theorem to me. Anyway, that's one result. And then another result is we tried to...
Nice question about this theorem. So, but for example, what functions are allowed? Can I define a function mu of x to be equal to runtime for this algorithm with input x?
And we call that the canonical condition.
Yeah, but
So in that case,
you take log. Right? But then I guess I can take exponential of your canonical condition.
Yeah.
And then I will be always polynomial.
That's right, that one will be polynomial.
So that's
But it's not NP complete.
Because you have only, okay.
But it's not NP complete.
I see.
So you'll find out some functions will definitely put any problem in polynomial class. But they won't be natural functions.
All right.
Good, no, that's a very good observation. So anyway, this is true. And now if we try to go to approximate computations, so now approximate computations, we're going to try to compute things up to epsilon. And what we're going to do is we're going to try to now make the cost. So we're going to compute up to, in floating point numbers, up to relative error, epsilon, but only using floating point numbers. And then the cost will now, or the time, which will be the cost, should be now polynomial in the size, which now includes the mu size. And the condition should be, the precision of the machine should be polynomial in epsilon. So that's why I think it's so long. Polynomial precision is, I think, as I was saying earlier, more or less anathema to numerical analysts. in numerical analysis, like a constant k, that's the worst that they want to think about. Maybe a condition number will change by a constant. They don't want it to be quadratic in the condition number. That's really too bad for them. They don't like it. But in fact, I think so. A theory should be developed in which one is talking about single precision complexity. That should be a good. That should be a good theorem, a good theory to work out. But here we don't do that. We do polynomial. And in this case, what we get is that there is an NP-complete problem. So that's kind of surprising. Again, except now you have to be somewhat different. So when you have an NP-complete problem, we want to discuss the polynomial class. We only want to decide if the point is in the set, not if it's not in the set. And we don't want to make any errors. So these machines that are supposed to find the polynomial class and NP, well, there is this paper, Malajovich, and the archive. You can read about it all in there, but we have to change things a little bit because while you know the size of the input, you don't know the condition number. So the condition number is usually not known. So if you had an algorithm that would decide if X was in the set before you included the condition number, you knew what time it was supposed to stop by. So if it didn't stop and say yes, then you could say no. So you had a method of determining the complement from determining the set. But here, you don't know the condition number, so you don't know when it's supposed to stop. So what we've done in a bunch of examples, without the error analysis, even though it could be included, is we've shown that you can solve the problem like find the solution of a square system of equations in polynomial time input data. And then we said, but the input data includes the condition number, but the condition number itself, we can estimate the integrals of the condition number, and then we find the whole process is polynomial time on the average. So this solved one of Smail's problems. It was recently solved by Pierre Leibez. And the problem was, is there an algorithm which will find for a square system of equations a single solution approximate in average polynomial time? And there is such an algorithm, which is pretty shocking because already the Bezout number is likely to be exponential on the input side, so the number of roots is likely to be exponential. So you have to pick an element out of an exponential set already is difficult. So there is going to be a lower bound. It's not that you can do this in bounded time or anything, it's a definite lower bound. But in fact, it's because of the distribution of the condition number, it's because as opposed to the power method, you had to integrate the distance to 0. But in complex equations, the degenerate systems are codimension 2. So the distance to codimension 2 variety, epsilon is like epsilon squared. So now you can integrate it. You couldn't integrate 1 over epsilon, but you can integrate 1 over epsilon squared.
And did he actually produce an algorithm?
Yeah, he's got an algorithm. He's got a specific algorithm.
Okay, specific.
Okay, so now I wanted to talk about the relation now with this question to a number theory question, so I didn't know exactly what people's interests were. I hope this is clear enough? You can find these things. They're too technical to talk about in detail. There are technical points. So this theorem that there's an NP-complete problem, this one actually is only for inputs which are floating point numbers. It's not for all real numbers. you have to take input that's a floating point number, so you can input it exactly into the machine. Because of this problem about distance to the boundary, and making errors in computation. It's just too hard for me to see that you can compute your way through and you're making epsilon errors, except if you can keep it precise. So here's this thing. I'll just say we have a machine over C. Let me just describe the problem. It's a problem inside C. I give you a K, and I specify K by its binary expansion. So that's the hint I'm going to give you. I'm going to give you the binary expansion of numbers, but you don't have them to start with. I'm going to give you an X, I give you a K and C, and I ask, is X an integer between 0 and K? I ask you to build a machine over the complex numbers that will solve this problem.
What does between mean on complex planing?
Well, it's an integer. Is X an integer? So if it's an integer, it's on the real line.
But the K is complex.
No, okay, I'm sorry, K is in N.
I'm sorry.
Yeah, good.
Okay.
Good. Yeah, so K's, I
It's
give
a very nice complex.
Yeah. K, I give you an integer, and then I ask you to decide, is another number, a complex number, an integer, and is it between 0 and K?
I see. Okay.
And so we call this 20 questions, because this is a game you play with your kids in the car. You know, you're driving someone, they're getting very antsy, and you say, okay, I'm thinking of a number between 1 and 1,000,000. What is it? And then they say, well, is it bigger than 500,000 or less than 500,000? You answer that question, but you're not allowed to ask that question in C. You're only allowed to ask the question, is it equal to something? So, now, can you solve it anyway? Can these kids, do you get to the end of the trip? Or can the kids tell you, okay, now take this number, multiply it by 1,000, subtract 8, is it 17? And so, okay, we have a machine. And this machine is, this problem's an NP. It's pretty easy to see because you write the binary expansion of the number if it's an integer, and then you check if it's less than the binary expansion of K. So you've got it's simple to make algorithm to do this. You can't find the binary expansion though, because you don't have inequalities. So you're given you can be given the binary expansion as your clue, and then you check. So okay, this problem's an NP, and it should not be in P. And so this should prove that P is not NP over the complex number. So this is the question, P not NP over C. I mentioned an interesting theorem here that the answer to this question is the same over every algebraic field of characteristic 0. But we don't know that with characteristic 2. So that's an interesting question, I think. In characteristic 2, is the question P equal NP the answer the same over every algebraic closed field of characteristic 2? 0? Yes? I don't know. Anyway, so now you're computing something, you get to a branch node. What happens at a branch node? A branch node can only go down the equal to 0 side at a finite number of points. Because otherwise it'll be identically 0. So you computed a polynomial of a certain degree. How many equal to 0 points do you have? It's finite. Otherwise, you would get identically wouldn't branch. So what happens is, if you're going to do this in polynomial time, you have to, in polynomial time, compute a polynomial which has k roots. Now the question is, can you do that? These are k roots over the integers. So you have to do some work, and you see that if you can do this, you'll do it over the integers, and then you compute this polynomial. And what is this polynomial? The polynomial, you can start with 1 and p, and then every time you compute, you have your polynomial k equal the product of polynomial z and polynomial l, with that's either plus, minus, or times. And j and l are less than k. So that's what you're doing in these computations. And the question is, if or not k, let me call this n. So the question is, if you start with 1 and p, and you compute this way, polynomial, pk, in case k additional steps, how many integer roots can it have? Let's say this equals my polynomial f, the tau of f equals the shortest computation length. And this type of computation. And then the conjecture is the number of zeros, distinct zeros of f, is less than or equal to tau of f for some constant c. So just to see, this is the number of distinct zeros of f. So for example, suppose I give you a bunch of quadratic equations, and you compose them. You might have 2 to the n roots, because each one will give you 2 to the 1, 2 to the 1, 2 to the 1. At the end, you may have 2 to the n to 1, and that one may be the root of a polynomial, and so you've done it. Each one only took you 3 or 4 steps, so you've only got 3n steps. And you may have exponentially many roots. You certainly do for real polynomials, the Chebyshev polynomials. Are they x squared minus 1 over 2 or something like that? That's the double angle formula for cosine, is this? Who remembers the double? It's calculus. We all teach calculus. We have to know the double angle formula for cosine. It's not x squared minus 1 over 2 or cosine squared minus sine squared. Sine x squared, no?
I think it's 2x squared
2x
minus 1.
2x squared, or 2x.
Yeah, because I did.
And then there's a 2, then there's a 2, or no 2.
No, because Chebyshev only had first coefficient power of 2, right?
So there's cosine 2x equals this is cosine x.
Yeah.
Good. So this one clearly has, if you iterate, just iterate this polynomial n times, compose it as itself n times. So this takes 3 or 4 steps, and the whole thing then takes, I don't know, 3 n times 3n steps. It has 2 to the n 0. Why? Because this is the double angle formula. So if you have cosine 2 to the n theta equals 0. This is the double angle formula. Whenever cosine 2 to the n theta equals 0, then that number gives you a 0 of this iteration. So there are 2 to the n 0. You can take pi and divide it by all the ways you multiply 2 to the n, get a multiple of pi. So this, clearly, this one has 2 to the n zeros for the nth iterate, but they're real. They're not rational. And so, and certainly they can't be integers, because when you iterate one polynomial, large numbers get larger. So they can't become zeros after a time, they get larger. So all the zeros of the iterates have to lie in a compact region, so and if they're integers, they're finite. So you can't iterate an integer polynomial to get infinitely many zeros. I don't know if you can iterate, if you can compose quadratic polynomials and get 2 to the n 0. So this is this tau conjecture. I think it has some versions in other parts of more complicated places in algebra.
How big are the examples that you know of that? And gets up
So I
to,
can't get C more than 2. I think there are examples where you get C more or less 2, because you can evaluate, with fast Fourier transform, you can evaluate polynomial degree n and n points. So you can evaluate it and then translate the zeros. So you can get, you have n zeros to begin with, you now translate it n times, you can get n squared 0. But that's the only trick I know. I don't know anything where you can have 3 here. And then I wondered, can you, for example, compose integer quadratics? So you get one integer quadratic, you can have 2 roots. Maybe you can compose 2 and get 4 roots. I can do that. Maybe you can compose 3 and get 8 roots. I couldn't do that. So I asked Mel Nathanson, and Mel asked his buddy at Rutgers, I forget his name now. They could do 3 integer quadratics composed to get 8 roots. But they couldn't do 16. They couldn't do 4 integer quadratics composed to give you 16 zeros. And a graduate student in Buenos Aires did it with the help of a computer. So there's 4. There is an example where you can compose 4 integer quadratics and get 16 roots. But there's no example known yet where you can compose 5 integer quadratics and get 32 roots. So that's a good problem. It would be a way maybe towards disproving this conjecture, even though I didn't say that you had to, here you have to build them from 1. You have to build the constants they use. In this question with the quadratics, I'm letting you use whatever constants you want. So it's an easier question. And so that's a great problem. Another great problem. In some ways, it reminds me a little bit of the ABC conjecture, because it involves, see, if you multiply 2 polynomials, you don't add them up, you don't add any roots. So it means when you add 2 polynomials. So it's like adding 2 numbers, you don't know how many factors. So, but the ABC is more or less saying that you can't get too many factors when you add 2 numbers. This would say you can't get too many extra roots when you add 2 polynomials. Anyway, that's the other thing, and I think I took my 50 minutes. Thank you.
Thank you. More questions?
I have a question. So when you're computing with real numbers, so your entries are in real numbers, and the time is an integer value function of these real numbers. So
The time is not an integer value, it's just an integer value. Yeah, it's a function of these numbers, but yeah, but it's an integer value.
right, so then maybe can't you study that from the point of view of real variables or something, of algebraic geometry or something that isn't available in the discrete case?
Oh, we were hoping. Yeah, we were hoping. But so far, no luck. There was I think Steve did one case where maybe it was done a little bit better afterwards. So how many branching nodes you need if you're going to find roots of a single variable polynomial. So then he could do some algebraic geometry, algebraic topology computation, and say you have to have so many different domains of definition in order to get a section of this covering space, even approximately. So he could do an algebraic topology computation, and Vasiliev made it a little better. But I don't know too many things like that. There's the one I mentioned. If you're going to choose from a set of 2 to the n things, you have to do also something like log n branches. That was, I think, some of the computer scientists from Princeton. I forgot his name. So, but yeah, there are some things you can do with the real numbers. One thing good about it is the sets you are producing are semi-algebraic sets. So if you're doing the exact computation, you're in semi-algebraic geometry, and you can do various things about it. Like you can hope that you'll compute the homology groups and single exponential time. So that's things we can do. We can compute the homology groups and single exponential time, depending on some complexity parameter. So there's some things you can do. But it's amazing that there wasn't, the problem remains. I mean, you thought that maybe you'd find something that is special to this class. For the integers and regular unitary inputs are, P is not NP, you know that because Hilbert's notions like undecidable. So can't be decided the polynomial time, you can't even decide it. So over Z and over a bunch of other places, we know that P is not NP. And that comes from certain things about elimination theory. So there are structures where you don't have elimination theory, where you can't do this. So I think there's a chart in our book that tells you a bunch of things that you can and can't decide. But the D fundamental cases when you really have R or C open. Amazing. Most everybody really home. Thank you.
But
yeah, more questions.
yeah,
Good.
the examples you mentioned, how large are coefficients? I mean, like, can you fit in the page? Or
Well, the example, yes, the example of limits and errors, if you have that, they're very large. Coefficients are very large. The one about when you get C equal to 2 is just more or less up to k squared. So you'll find k squared roots, and I think the coefficients are no more than k squared, because take 1 to k and shift them over k times. So that's that one. C equals 2 is not bad, but anything bigger. And yeah, the coefficients are very big, so you think you'd have trouble making them. Particular case of this, by the way, is, see, if you're going to compute the polynomial, you can compute the constant term. So if you're going to compute 1 to k, you're going to compute k factorial. So you can't even compute k factorial in log k steps. So or even a multiple, so you might get a multiple of k factorial. So you can try to just prove, you can't compute a multiple of k factorial in log k steps. Polynomial log k. I like the polynomial question better because somehow it seems more mathematical to me. But I think in that same paper we talk about k factorial. You know, if you have a number and you can represent it in two different, as a sum of two numbers in two different ways. Then you can get, see, I have C equals A plus B. So then I take the polynomial Z and C minus Z. Something like that. And then this should be, I don't know, I always forget this trick. If you represent two different ways, then you get the two products are different. So now you can, if I have, I have n and n minus b. If I take the value at c, I get the c and c minus b is a. The other one, I forget. This was the trick. You write the number and it's a sum in two different ways, and then you can get two different inverse images of a particular integer for a quadratic. So that's how you can try to build it. You try to build this as writing numbers that add up to the same number in a lot of different ways, But then it has to keep going on as you go down. What is that? You remember?
I remember you showed it, but I don't remember what the was.
Right. Okay. Yeah, so that's a nice thing. Quadratics are 2 to 1, but not on the integer.
It looks like real inputs is a different ballgame. In particular, you cannot get the classical complexity theory as a special case in this one because they consider a different class of problems. Basically, on the philosophical level, the input in the complexity theory, there are finite strings, known unlimited, of things, and each thing is finite. And here, each thing is infinite because it's a real number. So you have to consider it uniformly. You have to consider the things you compute as a function of this axis. And it's not how the classical complexity, in classical complexity you're not considering, you need to compute this function.
Z2 is the same.
Is the same? Absolutely yes, but the answers which you provide, they don't cover the answers which you provide with this stupid coding and all this kind of things.
No, these are made for the reals instead of Z2.
Instead of Z2, if you consider only your theory, can you now forget about the classical PNP things?
Well, it is the classical PNP theory for Z2. If you use Z2 here, it is the classical theory. And anything that a Turing machine can do can be done by a real number machine. So I don't know any NP-complete problems over the integers that land in P with a real number machine. I don't know an example like that. Maybe there is one. Some of the decidability changes because you can set an integer by coding the real number with the n.
Exactly. This
But
is
that's
kind of
decidability,
tricky.
but it's not polynomial time decidability because it takes all that time to read the number. So,
You can go, you take something like the change in omega, it's just one number, and the dimension is just nothing, and then, but that's an infinite information, and you can encode, and if you assume this is given, then whatever, just a very quick read, you go to the bit which you want, and you'll get it. These kind of tricks, they're not reflected in this theory, it's an honest computability theory, whereas the tricky ones, that's what I think.
even so, I still don't know any NP-complete problem that can be solved with a real number machine any easier. Not in polynomial time. I don't, because reading the bits takes time. We've got to multiply, go over, compare, multiply, compare, multiply, compare. It takes a long time to read the bit. So,
I agree, my example is more about decidability.
yes, decidability is very different.
But
It'd be interesting to have an example of a problem that's NP complete.
we have to make things more precise. Probably we reached the limit of where the exchange of ideas. to read the definitions and to make it explicit, more precise.
We don't know that the NP complete problems over, the usual NP complete problems are NP complete in this theory. So linear programming, we don't know that linear programming is NP complete. On the other hand, integer programming, I don't think we have an algorithm to do integer programming. It'd be interesting. I don't know. I don't know an example, and I think it would be interesting to have an example. I think we have a bunch of theorems where you can start. What's the difference in this machine on an input?
Yes.
So the difference in this machine is that you might have some constants in the machine. Otherwise, you have no constants, you're just doing the same operations, and it's no different. So the only difference is you're providing yourself with a finite number of constants. But now if you're only operating on integers or rationals or even a finite extension of the rationals, you start eliminating these constants. Because some of them are transcendental over and then they can't help you in branching. So the branching structure, initially you get rid of the transcendentals. And then you say, well, if I only got algebraics left, well, those live in finite extensions, which I can model by linear algebra. So I get rid of all the constants. So now I'm just left with a machine that works. So it's not clear to me that you can gain anything with the real numbers in the classical problems with respect to complexity.
If you're not cheating with definitions, then probably not. But
Yeah, but equal, say with the equal machines, equal over C. Over C, well, here's a different question that I wonder about a lot, because it's actually kind of a question that's asked a lot in mathematics. Over C, the witnesses are the roots of the polynomial system.
yeah,
So the witnesses have the cardinality of C.
okay.
Might there be a countable cardinality set of witnesses that work for all polynomial systems? So for example, you might imagine, one of the fantasies of many subjects, there'll be a countable number of invariants that classify singularities. Singularity theory was looking for countable invariants. They were looking for countable invariants to classify differential manifolds. They wanted to have a countable set of invariants. So that if you had a very good description of the type of singularity the system is presenting, you might be able to design something to test it. So it's conceivable to me that you might have a countable change of cardinality in the witness set. That's like P equals NP in the classification. You want to go from 0 to 2. Right? Here, can you go from uncountable to countable? I really don't know. There's a lot of work in logic these days about Borel structures and what can be done that might have something to say about a question like that. That's another thing. Can you change the cardinality? The witness set has a natural cardinality. And that would mean you've got a terrific classification thing in hand if you've got that.
Pretty coarse, but theoretically very,
Oh,
very
yeah.
attractive.
Yeah.
More questions?